Okay, let's get started. First of all, I want to apologize for the inconvenience in recent weeks. Hopefully tomorrow, since we're gets back to normal, we will have our in-person class tomorrow. So today we will keep talking about heap exploitation or heap-based buffer overflow. So buffer overflow are basically the same on heap as they are on stack. You override something with something bigger than the space is. So you override other important data, control data on the memory. However, there is no solution like a heap cookies right now, or because there's no return address to protect. There are several other reasons as well. In real world, stack is used in every application because dynamically create spaces in the memory. A lot of high-level languages like C++, Java, those kind of things, they use this kind of features automatically. So you do not sometimes think about it, you are using a heap. And in those object-oriented languages, in their objects or structures, it's very common to find the function pointers. And we already know that a function pointer is basically control data. It's kind of like the return address. It's a control pointer, right? So those are very sensitive information. If you override that to a malicious location, then you can execute malicious programs. So let's take a look at several examples. So this one is a very simple heap overflow example. We define a function here called fly. This function basically just print out flying. Then there is a structure. So what I have here is still C code. This is not C++ code, but a C++ code will be similar. So at the beginning, we have a function pointer in the structure. So if this is a 32-bit program, the function pointer itself is 4 bytes. Then we have 20 bytes of character arrays. We call it the name of the airplane. So this is a structure, name of airplane. It has a function, and it has a name. Then in the main function, what we do is we first print out the function fly's address. We also print out the function print flags address for you here. Then first, we create one structure. We created the first airplane. So we use malloc, size of the airplane. Then after that, we get the address. We print out the airplane one is at which address. We do the same thing again to get the second airplane structure and print out its address. Then both functions, both structures, we set their function pointer to fly. Okay. Then after that, we try to set the name of both airplane. We've set the second airplane's name first, which we input from stdin get 10 bytes. So there's no overflow, right? The second one, we set the first airplane's name. However, there is a bug in the code. We're actually retrieving 50 bytes from stdin. And we already know that the name here is only 20 bytes. So it's very likely we're going to overflow something on the heap because those two objects on the heap. Then after that, we will call those two functions again. After that, we freeze it. So as an attacker, our goal is capture the flag. So let's say, how can we capture the flag with this one? So let's look at the memory of this program. We're going to look at the heap, okay? So here we have the lower address, and the upper we have the higher address. So we already know that from the previous class, the heap structure actually look a little bit different than the stack object, right? So there are some meta information to do housekeeping work for the heap objects. And we know that there are 4 bytes of pre-size and 4 bytes of size of current data if this object is used. So the airplane 1, when we created this project, its data on heap will look like this. First is 4 bytes of previous chunk data size, its own data size. Then after that, it's actually its content. It has 4 bytes of the function pointer and 20 bytes of the name. So after that, we create the airplane 2. So the airplane 2 may be located right after airplane 1. It's possible, okay? But sometimes it's not. But since this program is so simple, it only has 2 objects, so it's very likely this case. So if airplane 2 is located after airplane 1, it will have the same structure. 4 bytes of pre-size, 4 bytes of its own size, 4 bytes of its first member, and 4 bytes of its second member. So you say there is a vulnerability here, is this fgets. First, we set the 2 objects function pointer to fly. So we're going to set this part to fly and this part to fly. Okay, there's no overflow. Then we're going to get the name of the second airplane. So we're going to put the second airplane's name here in this object. Okay, remember this is high, this is low. Okay, so lower flow. However, this one, if we do fgets, we write things into airplane 1's name, which is here. And we're going to override 50 bytes. So what will happen? It's very likely we're going to overflow the entire thing of airplane 2. We can overwrite everything of airplane 2, including those metadata and its members, which means we can overflow this control pointer, this code pointer. So when P1 executes this, it can execute the fly. However, when P2 executes this function, it doesn't execute fly. It can execute anything we write it to. Okay. Any questions so far? I think this part is relatively easy to understand. Does everything make sense so far? Okay, so what we're going to do is we are going to override name, override the whole thing. So those 2, we don't care about what we are going to overwrite. We just consider them garbage for now. But this part is what we are going to override the return address. So let's do this in the server, in our server. Okay, we have an overflow challenge 1. Let's say if we run this program, the program will print out fly is at this address, print flag is at this address, airplane 1 is at this address, airplane 1's name is at this address, and airplane 2 is at this address. So you can see that between airplane 1 and airplane 2, that's how many bytes? That's actually 32 bytes. Between the name of airplane 1 to the beginning of airplane 2, we are talking about like 28 bytes, something like that, right? So if we just type some names, let's say the first airplane, let's say it's Boeing. The second airplane, we say Airbus. They're just flying. There's no problem. But if the first airplane we have given a long name, there will be no it will be inputted twice, but no overflow. But if the first airplane, we just give a short name. The second one, we give a long name. What will happen? We're going to override this. We're going to override this with a 41, 41, 41, 41, which is ASCII of character 1 here. And later, when that one function is called, there will be a segment fault because we are trying to execute from address there's no code. Or if that doesn't happen, then later, if it's free, because we overwrite those data, where that one will also trigger some problems. Let's say, let me go back here. So let's do this. Say we get a segment fault. So how do we exploit this to print us the flag? It's actually very simple. Any ideas?
In the address of P function, we can just give the address of our print flag.
Yes, exactly. So how do we do that?
Fill in the metadata with garbage, and where the values of P function is, we have to give the address of our print flag.
Okay. So what we're going to do is here, the program is asking for 2 input, right? And the input is divided by a new line, right? So what we can do is we give a garbage like this. There is a /n. So we can, basically we can set the name of the first airplane, right? Now after that, we're going to, we set the name of the second airplane actually. The second airplane first, yeah. Now we're going to set the name of the first airplane. Then we have we will have 28 bytes of garbage, right? Because the distance between the name and the next one will be 28. Then after that, we just put the address of print flag, which is CD625556. That's it, right? That is our exploit. And when we do this, you see, we get the flag. And why we are not getting segment fault here instead we get this. Can anyone explain to me? What do you
Because
say?
print flag is a valid function.
Yes, print flag is a valid function, but let's see here. We overwrite this part, this part, this part, and this part, right? Print flag is a valid function, so when we call this one, we get a flag. However, later there will be free P2, right? But this part we already overwritten. This part, those 2 parts. Those are important. And also this part. When we consider something as a free, remember last class, there will be a doubled link at this space. Those are important metadata. But now when we get here, when we try to free it, the free function will check those metadata, including the double link. Then it says that this data, this object right now is not in the double link. You are trying to free an object that probably has been freed before. Anyway, it's not a valid object. It's not a valid heap chunk. That's why there is another protection mechanism, as you can see that they identify that there is they call this double free or corruption, then just abort. So this is also quite a new feature introduced in the last decades, I believe. Before that, double free has been a vulnerability we can exploit, but obviously in this version we cannot exploit that anymore. We can still crash the program, but not getting more. It's hard to get a shell or get a capture flag. Okay, so this is how we can get the flag of this simple example. Okay, next.
Sorry, Professor, can you please explain how we got the double free part again?
Double free?
Yeah, so the
This
double free or corruption. Yeah, why did that come again?
Okay, let's say how does the free function works. The free function will take one address. That is supposed to be the address of a valid heap object, right? How do we know if that's a valid heap object? Because those metadata should be reasonable. The size and the precise should be reasonable metadata. And what we have here should be the content of the object based on what we saw last class, right? So now those metadata have been overwritten. They do not make sense anymore. So the free function realize this is not a valid heap object anymore. Maybe it has been freed before, or maybe it has been memory corrupted. That's why it print out this double free or corruption. So technically, we're not doing double free here. You get it?
Yeah, thank you.
We're not doing double free, yeah. But if you get to really do double free, you get the same thing. Okay, so next we'll talk a little bit more about this double free, or it's called use after free vulnerability. So this is a class of vulnerability where the data on the heap is freed, but leftover reference, that leftover reference is also called the diagonal pointer, is used by the code later as if the codes are still valid, okay? Because completed programs, they use a heap a lot, and heap is really hard to manage because the developers, you have to maintain the heap. Whenever you do a malloc, you should do a free later. And you cannot do two frees, right? So it's when your program gets very complicated, multi-threading, everything, then things get very complicated and there will be a lot of errors. And it's possible that you use a pointer after it has been freed. And it's also possible that you double free an object, just as what we saw just now, okay? So let's take a look at what will happen if we use something and after we free it. So on the left-hand side, we have the memory map of a program. We focus on the heap part. So the heap where usually grows towards higher memory. This is different from stack where we go towards the lower memory. So let's say we create 3 objects on the heap. In 32-bit version, there's a 4 bytes of chunk size, another 4 bytes of a previous chunk size, then the data. So this is the first object, then third object, second object, and the third object. And in your code, there could be something, there could be a variable, could be a pointer, point to one of the objects, any of the object. So the pointer usually actually points to the code part, but you already know that there is metadata before that, right? So the pointer could be on stack, could be a global variable, could be from a different thread. All kinds of things could happen. So let's say it's a multi-thread program. One of the thread frees those 2 objects. So the second and third objects will be updated now. They are not valid data anymore. The previous chunk size will be updated. And here, we don't have the data anymore. Instead, we will have a double linked pointers here, as we discussed last week. So those 2 will be the same, right? But there's another variable on stack, which belongs to a different thread, may not know that those 2 has been updated. So they still point to here, that pointer variable, the pointer still points to the data here. And it may still use that data, okay? So when this happens, this pointer is called a diagonal pointer. So it's a leftover pointer in the code that reference freed data, and it probably will reuse that data. So there are different names for this pointer. Could be called a stale pointer or wild pointer. Then let's say what kind of issues this may have. First is the issue is if it still points to something doesn't exist, then it may generate, it may call to eventually call to a function that doesn't exist and just have a segment fault. Okay. Then segment fault basically is a denial of service attack. It can be even more serious if the attacker can control what to create on the stack. The attacker, let's say this part has already been deleted. Now the attacker create a new data here, and that new data, the attacker can set the value. Then later that data will be called by the old pointer and can do something malicious. So to exploit this kind of problem, the attacker usually need to allocate a different type of object over the one you just freed. So next we are going to look at one example code. So in this example code, we are simulating the attacker in this code. So this is realistic. It could happen in very complicated programs like browser, because for example, when your browser retrieves some new web page, it may create some data, new object on the heap. Or your JavaScript in your JavaScript code in your web page can directly create new data on the heap. So here we simulate this in one single C code and say why this could be a problem. So we still have the airplane here, the same structure, 4 bytes of pointer, 20 bytes of name, still have the fly function. Then we actually have a car structure, but I forgot to put the car structure here. But the car, let me check where I can get the car structure. It's on my GitHub. So heap 2, overflow 2. So you can see here, we also have a car structure. The car structure is a little bit different. It doesn't have a function pointer as its member. Instead, it has an integer. And the integer is how big the car engine is, the volume. Okay. But remember, the integer is also 4 bytes. The pointer is also 4 bytes. So they are the same size. They're just different type. And the name here also 20 bytes. So those two objects will take the same size. So what will happen here in this code is we first print out where fly is, then we print out where print the flag is. But instead of print out in the hex value, we print it in the unsigned int for you to easily use that. I'm going to show you how to easily use that later. Then first we create the airplane object, use malloc, and we print out where the airplane object is. Then we set the fly function to its code pointer. Then we call that code pointer, so we fly it. So after that, we free this object. Okay. Now P points to the airplane object is freed, but the value of P is not updated. P still points to that address. You see, P still points to the address, but the object airplane doesn't exist anymore. Next, we're going to create Oh, here I don't need to assign this to P actually. So anyway, here I'm going to create another object, which is car. The car object I will show you, which is also located at the same address because that chunk is available now. And the dynamic memory allocator will reuse that chunk. So the car will be placed at the same place. So now we input what the volume of the car is, and we just input the volume. Then we remember P, the type of P is still airplane, okay? So we can still call the function, which is a member of airplane. So when we call this function, what will happen? We're actually using the car object's volume as the address to call this function. Does that make sense? Let's show the demo here. We're going to use a 32-bit. We run this program. So let's say, what is the volume of the car? Let's say the volume of the car was 30. What will happen when I do 30? Any idea here? Okay, so basically when we do 30, what will happen is 30 will be treated as the address of that function. So we are going to get a segment fault. However, if we set the volume as the address of the print flag, we just type the value here. It's just that simple. Then we can get the flag because that value, even though we are thinking we're inputting an integer, that value will be treated as a function address, and eventually that function will be called. That's how we can get the flag. I hope that makes sense to you. Okay, that's basically what we have. Any questions here? So Jisham, did you lost the connection just now? And the mouse?
Yeah, Professor, I was having some trouble with network.
Oh, I see. Okay, so do you guys see what's going on here? So when did you guys lose the connection?
Actually, even I lost the connection, and I lost it like right when you were
When you're opening the code from GitHub.
Oh, yeah, I see. Okay, then we can, okay, let me explain to you guys. So you say here we have two different objects. One is airplane, one is car, right? So the airplane has 4 bytes of function pointer. The car doesn't have that number. Instead, it has a volume. Let's say it's the engine's volume, right? However, those two objects, they are the same size. They are exactly the same size because the pointer is 4 bytes. The integer is also 4 bytes. Now, when we go back to this code, you can see here, first, we create an airplane object, and P is pointed to the airplane object. Then we set fly, then we fly it, then we free it. The problem here is after we free it, we didn't update P. We're supposed to update P to 0, right? So if we call P, then we know this program will crash or whatever. However, we didn't update it. P still points to a valid location on the heap. And that location used to be the object of airplane, but that doesn't exist anymore because we freed it. The metadata has been changed, the content has been changed, but the pointer still points to that. Then we malloc a new project, a new object, which is a car. I don't have to sign that one to P here. I need to update that later. Just forget about this part. Just think we are doing malloc. So because we just freed the previous heap chunk, the dynamic memory allocator will actually put the car at where the airplane was. It will reuse the same chunk. That is how most dynamic memory allocator implemented. Then we can set the volume of the car because we have the car now. When we set the volume of the car, it will be placed in the volume member object there. But however, P still points to the airplane. So we can still call the airplane, right? Call the airplane's flying function. And this is where things get interesting, because we're not actually calling the flying function. We're actually calling to the address where stores the car's volume. No. So if we do the demo, you can see that when we run this program, we set the volume. So if we set the volume as 30, what will happen? 30 will be treated as a function address and be called. So it will be a segment fault. But if we set the volume as the print flags address, we can easily get the flag. And that is the use after free vulnerability. Make sense?
Yes, Professor. Thank you.
Okay. Cool. Any other questions?
Professor, if we free the malloc, then how we will know that this is pointing to some address? I mean, like the value will be freed, right? We will be only having some double linked list in that current location. So how does p dot func this one can you show it? P dot p func? Then how we will know that this is an address location?
Well, the problem is the example. I should update the example a little bit. The example here is this is a debug. This is more like a development bug, right? So when you are a developer, when you write this piece of code, after this, you are supposed to reset P to 0. That's the first thing you should do. Because the free will not reset P. As a programmer, you should reset P to 0.
But the values will be changed there, right?
Value, which value?
Values on heap.
Value, the free will change the value on the heap, yes.
But the next step, if you do malloc size of car, then we will actually, what will be there on heap then?
That will, at the location where used to be the airplane, we have a new object, which is a car.
So even for car, struct car, we have an function called pfun?
No, it doesn't. However, your pointer, the car doesn't have that, but everything is just a number, right? So the car doesn't have a function pointer. It only have a integer. But the pointer here we have, the P, we never change that. It's still the type is still airplane style. It still points to the airplane. So it can call this function. At a second level,
so it treats p.pfun as an function address.
It treats the volume of the function address.
Okay, now I got it.
Yeah, it treats the volume member of car as the function pointer member of airplane.
Because previously it used to be in function pointer, but since we freed that one, but we haven't changed the pointer. So
that pointer value may have been updated. It's possible it has been updated. It's maybe updated into some garbage, which will trigger segment fault. Okay. But what we did here is we set the car's volume. but we're not really setting the cast volume. We set the cast volume as the address of the function print flag. That's what we're doing here. See, we know the function address is here. Okay, I printed it as a decimal so we can input. So now we're setting the volume. You think we're setting the volume? We do 60. It will get a segment fault, right? Because the 60 will be used as a function address. Make sense?
Yeah, Professor, now it makes sense.
Yes. So if we set it as a print flex address, then it will just call that function. Yeah. Yeah, the example I'm showing here is not ideal. I will update that a little bit. Yeah, we can update it now actually. I mean, we have some time. So let's see how do we.
Professor, I have one more doubt there. Like,
Go ahead.
yeah, can you once go to the C code like which you were showing?
Yes.
Not this one in the slides.
Okay.
Yeah. So after this free of P, we don't have the reference of this airplane in the heap, right?
I don't understand what you mean by that.
So
After the free, the object on the heap is freed. It will be updated, but the pointer P still refers to that address.
okay.
Yeah.
So the next point, like malloc size of car, what this does, like I want to know, like what are the changes done in the heap after this line?
Well, this is exactly what happened before. We explained this. So when you first create, we use this one. When you first create an airplane, and then let's use this one. When you first create an airplane, it will have a structure like this: previous chunk size, data. The data has 4 bytes of name, 20 bytes of 4 bytes of pointer, 20 bytes of name. Okay. Then we free it. After we free it, the previous chunk size will be changed. The chunk size will be changed. That 4 bytes of pointer doesn't exist anymore. Instead, it will be the new data of the double link to have the freed list. So it will be 4 bytes of the freed list double linked, as we showed you in the last class. Other parts of the name will not be changed. Then we create a new object car here. Then this part is restored with valid information. This part is restored by valid information. However, those 2 parts, we haven't set a new value yet. So we are setting the volume as the address. Now the old pointer still points to here, and the old pointer thinks this is not a car. This is still an airplane. So it can still call this as a function. That's where the problem is.
Oh, okay. Yeah, got it.
Okay.
Thanks, Professor.
Yeah, I should change this code a little bit. Let's just do it here together. Yeah. Let's just do the web version. Makes sense easier. So here we actually should use different. We should not use P. We should use P1, right? So car, structure car, P1, then this one, then we put P1's address. So you will notice that P and P1 will have the same address, but P still points to that. So then we just here we just need P1 volume to this. Okay, this makes much more sense. Now we are calling P's this. Then when we free this, yeah. So this makes more sense. I should have the code like this.
Second time we had to free P1, right?
Technically, it doesn't matter. It will be the same thing, because P1 and P has the same value.
Okay.
So no matter which one you free, it's the same. That's a good thinking, but you can think more about that. Yeah. Okay. Cool. That's all I have for today's class. Any other questions? Okay, if no other questions, I see you guys tomorrow. Tomorrow we're talking about cache. See you. Thank you, guys.
Thank you.
Thank you, Professor.